When we say James Clerk Maxwell unified electricity, magnetism, and light into one complete theory, it sounds like a neat scientific phrase, but the truth behind it is far deeper, richer, and more revolutionary than most people realize. Before Maxwell stepped into the picture, electricity and magnetism were like two powerful but mysterious creatures wandering the scientific landscape with no obvious relationship. Scientists had poked at them, measured them, experimented on their behaviors, and built simple devices with them, but nobody had managed to explain why they existed or how they might be connected. Think of the world before Maxwell. Electricity was known mostly through sparks, shocks, batteries, and strange laboratory demonstrations. Magnetism was known from compasses, lodestones, iron filings, and the invisible pull of the earth. And light was treated as its own separate entity, a wave, yes, but of what? It traveled through space, it bounced off surfaces, it reflected, refracted, made rainbows, and revealed color, but no scientific theory tied it to anything more fundamental. These three forces were like separate languages being spoken by nature, each beautiful but isolated, each powerful but not understood as part of a larger message. Scientists could listen, but they couldn't translate. Maxwell was the translator, but his translation didn't happen overnight. It started with decades of experiments done by scientists before him. Faraday, Ampere, Coulomb, Gauss, Oersted, all of them had found clues, pieces of the puzzle. You can imagine a massive jigsaw lying across a table, with bits filled in here and there, but no one able to see the full picture. Faraday, in particular, had discovered that moving electricity creates magnetism, and that moving magnetism can induce electricity. But he described these discoveries visually in the form of lines of force, shapes he imagined existing in space. To many mathematicians, his ideas seemed mystical or unclear because they weren't written in equations. Maxwell, though, was different. He had the rare ability to think like a mathematician and visualize like Faraday. Where most scientists either calculated or imagined, Maxwell did both at the same time. It was like having two superpowers. He could take Faraday's intuitive sketches and convert them into precise mathematical language, giving them clarity and structure. He wasn't just solving problems. He was cracking open the hidden code of the universe. As Maxwell explored the relationship between electric and magnetic fields, he discovered something stunning. The two were not separate forces at all. They were two sides of the same coin, deeply intertwined, constantly influencing each other, and capable of propagating through space in a self-sustaining dance. He realized that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. This discovery might sound abstract, but it's the core mechanism that allows waves to exist in the first place. Imagine a ripple moving through a calm pond. Now, instead of water waves, envision two invisible fields, one electric and one magnetic, pushing and pulling each other forward across space. Maxwell saw this interaction as a wave, a self-propagating, ever-sustaining pattern moving through the void. This was a revolutionary thought, because once he calculated the speed of these waves, he found a number that should have made the world gasp: the speed of light. Light wasn't just something that came from the sun, candles, or bulbs. Light was an electromagnetic wave, a wave created by interacting electric and magnetic fields, a wave that didn't need a medium, didn't need air or any physical substance, because the fields themselves carried the wave forward. Light, something humanity had known and observed forever, was suddenly part of the same family as electricity and magnetism. In that one realization, the universe snapped into focus in a way it never had before. Maxwell had connected three great forces into one unified picture, creating what we now call classical electromagnetism. If the universe were a symphony, Maxwell had discovered the sheet music. If the universe were a computer, Maxwell had uncovered the source code. This was more than a scientific achievement, it was a philosophical shift. Before Maxwell, nature looked fragmented. After Maxwell, nature looked coherent, elegant, and deeply interconnected. His equations didn't just describe behavior, they predicted new phenomena. They revealed that the universe allowed electromagnetic waves of all different frequencies, not just the narrow band of visible light. This prediction set the stage for later discoveries: radio waves, microwaves, X-rays, gamma rays, and more. Maxwell had opened the door to the entire electromagnetic spectrum, even though he never lived to see these technologies built. One of the most mind-bending parts of Maxwell's work is the simplicity hidden inside the complexity. His full mathematical system originally had 20 equations, but later physicist Oliver Heaviside reduced them to four equations that could fit on a t-shirt, yet describe almost everything about electricity, magnetism, and light. 4 equations that power our world today. These equations explain how antennas send signals, how motors rotate, how transformers work, how power travels through cables, how light moves through space, how MRI machines image your body, and how Wi-Fi transmits across your home. Yet, despite all this, Maxwell himself wasn't after fame or recognition. He was driven by curiosity, by a deep internal need to understand the logic of nature. While others chased notoriety, Maxwell chased truth. He spent long hours buried in notebooks, exploring ideas, testing assumptions, and following the implications of his mathematics wherever they led. His unification of electricity, magnetism, and light wasn't just an intellectual victory. It was an expression of his belief that the universe must make sense, and that human minds, with enough creativity, patience, and imagination, can uncover that sense. His work influenced almost every major scientist who came after him. Einstein once said that his own work on relativity was built on Maxwell's foundations. When Einstein developed the idea that nothing could travel faster than light, that light had a fixed speed, he was relying directly on Maxwell's discovery that light is an electromagnetic wave with a specific speed determined by electric and magnetic constants. In a profound way, relativity exists because Maxwell first showed that the speed of light isn't random. It's woven into the structure of reality. Maxwell's achievement also marked the beginning of modern field theory, one of the most important ideas in physics. Instead of explaining forces as objects pulling and pushing on each other from a distance, Maxwell described the world as a system of fields filling space. These fields have energy, they carry momentum, and they can interact even when nothing material connects them. This was a radical departure from Newton's vision, and it paved the way for the quantum field theories that make up modern physics today. To fully appreciate Maxwell's unification, it helps to imagine life without it. No wireless communication. No electric power systems as we know them. No understanding of how light works, which means no lasers, no fiber optics, no digital displays, and no modern imaging. So much of our world relies directly or indirectly on Maxwell's insights that if you removed his contribution, modern civilization would fall apart like a Jenga tower with its core blocks missing. And yet, despite his colossal impact, Maxwell is often less well known than Einstein or Newton. His name doesn't appear in casual conversation. His face doesn't appear on posters or t-shirts. Earths at the same popularity scale. But in the inner circles of physics, he is revered. He is the bridge between classical and modern science, the one who expanded the boundaries of what physics could explain. The beauty of Maxwell's unification is that it didn't just explain what scientists already knew. It predicted what they didn't. It told them that electromagnetic waves must exist, even though nobody had ever seen or generated them. It took more than 20 years after Maxwell's death for Heinrich Hertz to create the first radio waves in a lab. When Hertz succeeded, he said something almost poetic. "I have no use for them," referring to the waves. But others did, and soon enough, the world did too. Maxwell's equations were like seeds planted in soil that hadn't yet been watered. When the era of engineering arrived, those seeds bloomed into radio, television, radar, computers, and the Internet. He didn't build these technologies himself, but he built the understanding that made them possible. It's like he handed humanity the blueprint for the technological future, one elegant equation at a time. Maxwell's unification was not just about connecting three forces. It was about demonstrating a deeper idea that nature, at its core, is built on unity. Patterns seen in one area often echo in another. Forces that appear different may be manifestations of the same underlying phenomenon. His work encouraged scientists to search for grand unifying principles, a quest that continues today in theories like the Standard Model, string theory, and the ongoing search for quantum gravity. In essence, Maxwell didn't just unify electricity, magnetism, and light. He unified how we think about the universe itself. To continue understanding the true depth of Maxwell's unification, it's helpful to step inside the mindset of scientists living in the 1800s. At that time, the dominant view of science was shaped by Newtonian mechanics. Objects moved when forces acted on them, and those forces were transmitted either by contact or across empty space. But no one really understood how a force could act across emptiness. What makes a magnet pull a nail even when they aren't touching? What allows a charged balloon to lift small bits of paper without any physical link? Why does light travel through space when space is supposedly empty? These were questions that seemed almost mystical. Maxwell shattered the mystery by providing a physical, mathematical, and conceptual framework that explained these invisible interactions not as actions at a distance, but as behaviors of fields that fill space. When you place an electric charge somewhere, it creates an electric field everywhere around it, not just nearby, but extending outward infinitely. When you move that charge, the electric field changes, and this changing electric field creates a magnetic field. The magnetic field, in turn, can change and generate a new electric field. These interlocking behaviors ripple outward, forming a wave that moves on its own, independent of the original source. This self-sustaining ripple is what we call an electromagnetic wave. In other words, Maxwell didn't unify three forces by simply stating a fact. He showed mathematically how one phenomenon transforms into another. Electricity generates magnetism, magnetism generates electricity, and their continuous interplay generates light. That's not just unification, that's revelation. Part of the beauty of Maxwell's insights lies in the creative leap he made, a leap others weren't able to make. For example, when Faraday looked at electromagnetic induction, he saw moving magnetic lines of force creating electric currents. But Faraday didn't use equations. Maxwell believed in Faraday's vision even when others dismissed it as primitive or non-mathematical. Maxwell's trust in Faraday's intuition became the foundation of modern physics. He translated Faraday's sketches into mathematics, much like translating a poem into a symphony without losing any meaning. This translation process is where Maxwell's genius shines most brightly. He realized that if Faraday was right, that magnetic influence spreads throughout space, then space itself must be active, not empty, not passive. Something must exist in the void that allows these influences to propagate. Maxwell called this conceptual medium the electromagnetic field, and once he did, the universe changed forever. Physicists no longer had to imagine forces traveling through nothingness. They could now imagine fields permeating space, fields that carry energy and momentum, fields that can exist even in perfect vacuum. This idea laid the foundation for almost everything that came after, including relativity and quantum physics. Maxwell's fields were the ancestors of modern quantum fields, the building blocks from which particles and forces arise. If Maxwell had not introduced the field concept, physics would never have evolved into the form we know today. Einstein often said that his own theories were simply refinements of Maxwell's ideas, extensions of the framework Maxwell built. Another profound aspect of Maxwell's unification is that it made light no longer mysterious. Before Maxwell, scientists could describe how light behaved. It refracted, reflected, interfered, but the question, "What is light?" had no answer. Some thought it was made of particles. Some thought it was a wave in an invisible substance called the ether. Maxwell eliminated the need for any mysterious medium. Light was not a wave in some hidden material. It was a wave in the electromagnetic field. Light was not something separate from electricity and magnetism. It was made from them. This understanding meant that light was no longer unique. It wasn't a special, magical phenomenon. It was just one type of electromagnetic wave. There could be many others, and Maxwell's equations predicted them. The only difference between visible light and non-visible electromagnetic waves was frequency and wavelength. This prediction opened the door for the entire electromagnetic spectrum: radio, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of them hidden from human sight, but all of them natural consequences of Maxwell's mathematics. In a sense, Maxwell expanded human vision. He showed that nature was humming with waves everywhere, at frequencies our eyes simply couldn't detect. Scientists later built instruments to see these invisible frequencies, leading to technologies like radio telescopes, radar, microwave ovens, and medical imaging. All because Maxwell had the imagination to ask whether light was just one part of a much larger phenomenon. It's also important to understand that Maxwell didn't just unify electricity and magnetism as concepts, he unified the equations themselves. Before him, there were separate laws: Coulomb's law for electric charges, Gauss's law for electric fields, Ampere's law for currents, and so on. Maxwell realized that some of these laws were incomplete. One famous example is Ampere's law, which stated that magnetic fields are generated by electric currents. But Maxwell realized something subtle was missing, a correction term required to preserve the consistency of the equations. This correction term, called the displacement current, seems like a tiny detail, but it was the key to everything. Without that term, electromagnetic waves wouldn't emerge from the equations. Without that term, light would not arise from the math. Without that term, the universe would look disconnected and chaotic. Maxwell's correction turned the equations from a collection of awkward rules into a single, symmetric, elegant framework describing a unified force. Imagine writing a song with many instruments playing different parts. It might sound messy until someone adds one missing chord, the one that ties the melody together. Maxwell added that chord, and suddenly everything harmonized. One thing that makes Maxwell fascinating is how ahead of his time he truly was. His predictions were so bold that many scientists didn't know what to do with them. They accepted that his equations worked mathematically, but they couldn't believe that waves of electricity and magnetism really traveled through empty space. It wasn't until Hertz experimentally generated radio waves in 1887, long after Maxwell had passed away, that his ideas were confirmed. And once they were confirmed, it became clear that Maxwell had essentially invented the theory behind radio decades before anyone even dreamed of broadcasting sound through the air. His influence didn't stop with radio. When engineers like Marconi and Tesla began creating the wireless world, they were effectively applying Maxwell's theories in practical form. Every modern communication technology, television, Wi-Fi, Bluetooth, cellular networks, satellites, is animated by the same principles Maxwell discovered. Think of Maxwell's work as the foundation of a massive technological skyscraper. The skyscraper may have hundreds of floors, filled with thousands of inventions, but without Maxwell's foundation, none of them could stand. Another way Maxwell unified science was by establishing a consistent system of units and constants. When he derived the speed of electromagnetic waves, he used values for electrical permittivity and magnetic permeability, two constants describing how electric and magnetic fields behave in space. The fact that these constants predicted the speed of light was a mathematical miracle that stunned the scientific world. It meant that the universe had built-in properties that dictated the speed of electromagnetic waves, and therefore the speed of light. This idea profoundly influenced Einstein. If the speed of light was determined by the electromagnetic properties of space itself, then it shouldn't vary depending on an observer's motion. This became one of the cornerstone ideas of special relativity. So, when we talk about Maxwell unifying electricity, magnetism, and light, we're also talking about Maxwell indirectly paving the road for relativity, which reshaped physics forever. Another stunning consequence of Maxwell's work is the realization that energy can be carried through space by electromagnetic waves. Before this, people believed energy could only travel through matter. Maxwell showed that fields themselves could carry energy. This changed everything. It allowed scientists to understand how the sun's energy reaches Earth, how radiation transfers heat, how antennas transmit signals, and how electromagnetic waves can move through vacuum without any medium. It's impossible to overstate how revolutionary this was. Imagine living in a world where people believed nothing could travel through empty space except particles. Then imagine discovering that space itself carries energy and information across vast distances. Maxwell didn't just describe the universe, he rewired humanity's understanding of existence. Maxwell's contribution also reshaped engineering. Before him, electricity was mainly a laboratory curiosity. After him, it became the backbone of modern industry. Engineers built power stations, electric motors, transformers, and transmission lines based on the principles Maxwell uncovered. Even today, electrical engineers learn Maxwell's equations early in their training because every major electrical technology, from generators to electromagnetic sensors, depends directly on his theory. His unification even reaches into biology. Modern neuroscience relies on understanding electrical impulses in nerves, which behave according to Maxwell's principles. Medical imaging techniques like MRI operate entirely on electromagnetic interactions described by Maxwell. Fiber optic cables that carry internet signals use electromagnetic waves to transmit data across oceans. In short, Maxwell's unification didn't just connect three forces, It connected science to technology, theory to application, and imagination to reality. Another fascinating aspect of Maxwell's work is its aesthetic beauty. Many physicists describe his equations as among the most beautiful in all of science. They are symmetric, compact, elegant, and incredibly powerful. They show that nature is not chaotic and unpredictable, but organized and harmonious. In this sense, Maxwell did not just unify forces, he revealed the artistry of the universe. His equations read like poetry written in the language of mathematics. Maxwell himself was humble about his achievements. He was not one to boast. He often downplayed the significance of his discoveries, even as they transformed the scientific world. But Einstein, who had a keen sense of scientific greatness, openly said that Maxwell's work was the most profound and the most fruitful that physics has experienced since the time of Newton. Today, when physicists dream of unifying all the forces of nature into a single framework, they are following in Maxwell's footsteps. His unification proved that seemingly separate forces can emerge from one underlying principle. It inspired the search for deeper connections between electricity and magnetism, between relativity and electromagnetism, between quantum mechanics and classical fields, and ultimately between gravity and quantum field theory. Maxwell started a tradition of unification that continues to this day. In the grand story of science, Maxwell stands as a turning point, a moment when humanity discovered that the world is simpler, more structured, and more interconnected than it ever seemed. Electricity, magnetism, and light, once treated as strangers, were revealed to be siblings. The universe became less mysterious and more elegant, and our ability to harness nature's power exploded. Even now, when you turn on a light, unlock a phone, connect to Wi-Fi, send a message, watch a video, or use literally any electronic device, you are living inside Maxwell's universe. His unification is embedded in the circuits, antennas, signals, processors, and screens that shape modern life. He took invisible forces and revealed their unity, and in doing so, he wired the world. Maxwell didn't just unify three forces. He unified the past with the future. He unified physical theory with technological innovation. And he unified our understanding of nature in a way that continues to illuminate everything we do. When we say that Maxwell's equations predicted electromagnetic waves, and that this prediction became the foundation of all wireless communication, we're talking about one of the rare moments in scientific history when pure thought, pure mathematical imagination, and pure creativity reshaped the physical world long before technology caught up. It's the story of how equations scribbled on paper quietly birthed the age of radio, radar, Wi-Fi, television, GPS, and the entire invisible web of signals that surrounds us today. But to appreciate just how monumental this truly was, we need to step inside the world before Maxwell made this discovery. Imagine a time when there was no radio, no telephones, no wireless signals of any kind. Information could only travel as fast as a horse, a ship, a letter, or at best, a telegraph wire. People communicated through physical objects, ink on paper, sound waves in air, mechanical vibrations through wires. The idea that a message could fly invisibly through space without any wires, without any medium, without any physical connection, would have sounded like fantasy or sorcery. Even the idea that invisible waves existed at all was beyond the imagination of most scientists. Light was the only known wave, and even that was poorly understood. Nobody thought it belonged to any larger family of waves. But Maxwell wasn't like other scientists. He saw nature not as a collection of disconnected phenomena, but as a unified system governed by deep mathematical harmony. As he worked through the laws of electricity and magnetism, he began recognizing something extraordinary. The equations were whispering about a hidden phenomenon. They were hinting at waves that nobody had ever seen, waves that could travel through space at a precise, predictable speed, waves that emerged naturally from the dance of electric and magnetic fields. To understand how Maxwell made this leap, it helps to picture what was known before him. Scientists knew that charges created electric fields, and magnetized materials created magnetic fields. They knew that moving charges created magnetic effects, and changing magnetic fields could induce electric currents. Thanks to Faraday, the link between electricity and magnetism was known, but the picture was incomplete, like having a map with several important cities marked, but no roads drawn between them. Maxwell realized that something critical was missing, a mechanism that made the equations self-consistent. When he introduced the displacement current, a mathematical correction that ensured everything worked smoothly, the equations suddenly became not just consistent, but astonishingly powerful. They went from being a patchwork of individual laws to a unified, elegant structure. And once they achieved this elegance, they revealed something breathtaking. Maxwell discovered that the equations allowed for waves, not material waves like those on water, but waves in the electromagnetic field itself. These waves didn't need air, water, or any physical medium. The fields themselves were enough. When the equations were solved, the waves that came out had a specific speed. Maxwell calculated that speed using known electrical and magnetic constants, and he found something eerie. The resulting number matched the measured speed of light. This wasn't a coincidence. It was a revelation that changed science forever. Light wasn't just some mysterious phenomenon. It was an electromagnetic wave. And if light was a wave, then the equations implied that there must be other electromagnetic waves too, waves with frequencies higher or lower than visible light, waves nobody had ever detected, waves that existed everywhere, waiting for someone to discover them. This prediction was pure imagination backed by mathematics. Maxwell didn't have the equipment to generate or detect such waves. No one did. For him to claim that invisible waves traveled through space simply because his equations said so was bold, almost audacious. But this belief, that the universe obeys mathematics deeply and precisely, is what separates visionary scientists from ordinary ones. Maxwell trusted his equations more than he trusted the sensory limits of human beings, and he was right. Now, imagine the significance of this. Before Maxwell, humanity had access to just one small window of the electromagnetic spectrum, visible light. We could see rainbows, reflections, shadows, and colors, but we had no idea that this narrow band of wavelengths was merely one thread in a vast, invisible tapestry. Maxwell tore open that hidden tapestry. He predicted the existence of an entire spectrum of waves, radio, microwaves, infrared, ultraviolet, X-rays, gamma rays, long before any experimental evidence appeared. He predicted these waves decades before anyone had devices capable of detecting them. This moment in science is similar to a composer writing a symphony for instruments that haven't been invented yet. Maxwell wrote the score, and future generations of scientists and engineers built the instruments to play it. But predicting electromagnetic waves was only the beginning. Maxwell also described how they worked. He showed that electric fields and magnetic fields weren't static or isolated entities. They could travel, oscillate, spread across the universe, and carry energy with them. This idea completely rewired our understanding of empty space. Space was no longer nothing. It was a stage on which fields could vibrate and propagate like ripples on an invisible ocean. Maxwell didn't just predict waves, he predicted propagation, and propagation is the heart of communication. Once a wave exists that can carry energy, information naturally follows. You can encode rhythm, pattern, vibration, and variation into these waves. You can modulate them, you can send messages across them. Maxwell may not have imagined smartphones or satellites, but the logic of his equations made such things inevitable. The universe itself permitted them. Only later did scientists like Hertz, Tesla, and Marconi realize that they could take Maxwell's waves and use them to bridge distances. Hertz was the first to experimentally generate radio waves in a lab, proving that Maxwell's prediction was real. But Hertz didn't see much practical use for them. He was a pure scientist. He cared only about confirming Maxwell's theory. When asked about the applications, he shrugged and said he couldn't think of any, but others could. Marconi, inspired by Maxwell and Hertz, built the first wireless telegraphy systems. Suddenly, messages could cross oceans without cables. Ships could communicate with shore. Armies could communicate across battlefields. News could cross continents in seconds. All of this came from waves Maxwell predicted using nothing but mathematics. It's wild to think that our modern world, where signals bounce between satellites, phones stream videos across continents, Wi-Fi routers push data through walls, Bluetooth headphones play music from across the room, cars navigate using GPS signals, and airplanes land using radar exists because one man stared at a set of mathematical equations and saw waves in the numbers. Today, electromagnetic waves are so deeply embedded in our lives that we forget how magical they are. When you send a message to someone, it travels not through wires, not through air, but on ripples in the electromagnetic field that Maxwell described. When you watch a video or stream music, your device is catching waves that originated miles away from routers, towers, or satellites, waves that oscillate billions of times per second. When you heat food in a microwave, when you let your phone's screen glow, when medical scanners peer inside the human body using X-rays or radio frequency pulses, you are interacting with parts of a spectrum that Maxwell predicted before anyone had ever encountered them. Maxwell didn't just predict waves, he predicted a universe full of hidden motion. The air around you right now is vibrating with radio waves from hundreds of stations. Your environment is filled with microwaves, infrared radiation, ultraviolet light, and cosmic signals from distant stars, all sliding through each other without interference, all obeying Maxwell's equations. We live in a sea of electromagnetic activity, and we barely notice it because our senses evolved only to detect a tiny portion of it. This is why Maxwell's work is considered one of the greatest intellectual achievements of all time. He didn't discover something directly visible or directly measurable. Instead, he uncovered the invisible architecture of reality, the blueprint for how energy moves through space. It's the difference between seeing the surface of a painting and understanding the techniques that created it. But what makes Maxwell's prediction even more astonishing is that it was done in an era with almost no supporting technology. He didn't have oscilloscopes, antennas, signal generators, or advanced mathematics. He was working with simple tools, simple equations, and the imagination of a deeply insightful mind. He built the theory that future generations would use to build technology he never dreamed of. This is the kind of mind that doesn't just understand the world, it expands its limits. Many physicists point out that Maxwell's prediction of electromagnetic waves is one of those rare scientific breakthroughs where theory outran experiment by decades. It's like predicting the existence of atoms without microscopes, or predicting gravitational waves before we had detectors like LIGO. Maxwell was operating on the frontier of knowledge, and he had the courage to trust the implications of his own work even before anyone could test it. Another way to understand the magnitude of this keynote is to recognize how it changed the human relationship with distance. Before Maxwell, distance was a barrier to communicate, to share information, to coordinate events. After Maxwell, distance became almost irrelevant. Signals could cross oceans instantly. Ideas could jump continents. Nations could connect in real time. The world became smaller, more connected, more unified, not politically, but physically, through the waves Maxwell predicted. The first wireless communication was essentially the first time humanity spoke through the electromagnetic field. And since then, we haven't stopped speaking. Billions of signals flow every second: radio broadcasts, television transmissions, satellite communications, airplane radars, medical scanners, computer networks, Wi-Fi routers, cell towers, GPS, satellites, space probes, all of them building on the framework Maxwell revealed. When historians talk about technological revolutions, they often mention the Industrial Revolution, the Digital Revolution, or the Information Age. But every one of these revolutions depends on the electromagnetic revolution that Maxwell initiated. His prediction of waves didn't just lead to new technologies. It changed the destiny of human civilization. Without Maxwell's waves, there would be no global information network, no space communication, no wireless anything. The modern world would be unimaginable. And yet, amazingly, Maxwell himself remained humble about his work. He knew that he had uncovered a profound truth, but he never portrayed himself as a revolutionary. In his letters, he described the process not as a triumph, but as a logical consequence of following the equations to their natural conclusion. This humility contrasts sharply with the magnitude of his contribution. It's as if he discovered a new continent, but treated it as nothing more than a nice walk in the park. Maxwell's prediction of electromagnetic waves is one of the greatest examples of the power of human thought. It shows that the universe is not something we merely observe. It's something we can understand, even in its invisible aspects, through the language of mathematics. As we move deeper into the impact of Maxwell's prediction of electromagnetic waves, it becomes clear that his discovery did not simply add a new chapter to physics. It completely reorganized the structure of human communication, engineering, and scientific understanding. What began as a mathematical insight evolved into a global transformation affecting every aspect of society. Maxwell's equations were not just about electric and magnetic fields interacting. They were about the realization that nature itself carries information, energy, and motion across space without any physical medium. This was the true beginning of wireless communication, the invisible bridge across distances that we now depend upon almost every minute of our lives. When Heinrich Hertz experimentally confirmed electromagnetic waves in the late 1880s, the world finally had undeniable proof that Maxwell had touched on a fundamental truth of nature. Hertz generated radio waves in a laboratory using sparks and oscillating circuits, showing that these waves behaved exactly the way Maxwell's equations predicted. They reflected, refracted, polarized, and traveled through space at the speed of light. Even though Hertz famously remarked that his discovery had no practical use, the seeds for innovation had already been planted. Maxwell's mathematics became the foundation upon which inventors like Guglielmo Marconi, Nikola Tesla, and later engineers and scientists built entire technologies that rewired the planet. Wireless telegraphy was one of the earliest practical results. For centuries, communication at a distance required carrying messages physically or using visible signals like flags or lamps. Maxwell's electromagnetic waves made it possible to send messages instantaneously across vast distances using nothing but energy. Ships could communicate across oceans without relying on wired connections. Military forces could coordinate in ways previously unthinkable. Governments, newspapers, explorers, and families began to operate in a world where information could travel faster than any human or machine. This shift changed political decisions, economic movements, and even the way global events were reported and understood. A message that once took weeks could now travel in seconds, reshaping how rapidly societies evolved. As radio matured, new possibilities emerged. Broadcasting transformed communication from a private exchange into a public, shared experience. Maxwell's predicted waves became the carrier of music, news, entertainment, and education. Entire cultures began to form around broadcasts, radio shows, debates, national addresses, and live music performances became part of a collective identity. People no longer felt isolated in rural or distant regions. Electromagnetic waves connected them to the heartbeat of their nation and the wider world. In many ways, Maxwell's prediction brought humanity closer together emotionally, socially, and intellectually. The evolution of radio opened doors to more advanced wireless systems. Radar, for example, relied on the reflection of radio waves to detect distant objects. This technology changed military strategy during World War II, allowing nations to detect incoming aircraft or ships long before they were visible. Radar saved lives, prevented surprise attacks, and played a crucial role in shaping the modern world map. The underlying principles came directly from Maxwell's equations: waves traveling through space, bouncing off objects, carrying information back to detectors. Without Maxwell's theoretical work, radar would have been impossible. As the 20th century progressed, humans discovered new regions of the electromagnetic spectrum. Each band microwaves, infrared, ultraviolet, X-rays, gamma rays revealed a new domain of technology. Microwave communication enabled long-distance phone calls without cable networks. Infrared communication allowed remote controls and early data transmission systems. Ultraviolet and higher energy waves opened new branches of science, from medical imaging to astrophysics. The electromagnetic spectrum became humanity's playground, and every tool built within it was a tribute to Maxwell. The invention of television marked another leap. Instead of sending just audio waves through space, engineers learned to encode visual information and combine it with sound. Entire scenes, stories, and events could be sent across cities or countries using electromagnetic waves. Entertainment industries exploded. Global news broadcasting became possible. Historical moments, moon landings, presidential speeches, world tournaments, were watched simultaneously by millions. Maxwell's waves had become the medium through which civilization shared its memories. Wireless communication continued to evolve. Satellites launched into orbit began relaying signals around the globe. The world grew smaller as long-distance communication became instantaneous. Suddenly, a message from one continent could reach another without touching a single wire on Earth. This leap made international business, diplomacy, and education faster and more interconnected. The GPS systems that guide our phones, cars, planes, and ships operate using signals that rely on Maxwell's predictions. Each satellite continuously sends electromagnetic waves to Earth, allowing devices to calculate their exact location. The precision of this system, down to meters or even centimeters, rests entirely on the behavior of electromagnetic waves described by Maxwell. Then came the digital revolution. Once communication shifted from analog signals to digital encoding, electromagnetic waves became even more powerful. Wi-Fi transformed homes, schools, and workplaces into interconnected ecosystems. Cell phones evolved into smartphones, sending and receiving billions of packets of information across invisible electromagnetic networks. Video calls, social media, cloud computing. All of these depend on high-frequency signals moving through the air according to Maxwell's mathematics. Whether we are streaming a movie, texting a friend, or navigating traffic using GPS, we are constantly interacting with technologies rooted in Maxwell's second keynote, his prediction that electromagnetic waves exist and can carry information across empty space. Modern scientific research also relies heavily on electromagnetic waves. Astronomers use radio telescopes to study distant galaxies, pulsars, and cosmic microwave background radiation, the faint afterglow of the Big Bang. These instruments detect waves that have traveled for billions of years through space, granting humans the ability to look into the deep past of the universe. Maxwell's equations guide the interpretation of these signals, helping scientists uncover the structure of galaxies, the behavior of black holes, and the history of cosmic evolution. Without Maxwell, our understanding of the universe would be shallow and incomplete. Medical technology has equally benefited. MRI machines use radio waves to create detailed images of the human body, helping doctors diagnose illnesses without invasive procedures. This life-saving tool is entirely based on electromagnetic principles predicted by Maxwell. The machine uses powerful magnetic fields and radio waves to interact with hydrogen atoms in the body, generating signals that can be converted into images. Every MRI scan represents a direct application of Maxwell's work to human health and well-being. As we push forward into future technologies, electromagnetic waves continue to expand their influence. 5G networks, with their ultra-high-speed communication capabilities, are built on sophisticated manipulation of high-frequency waves. These networks promise to support smart cities, self-driving cars, advanced robotics, and global automation. Space communication systems are becoming more complex as missions venture deeper into the solar system, requiring precise, long-distance electromagnetic links. Quantum communication technologies, while still emerging, also reference principles connected to Maxwell's foundation of field theory. What's truly remarkable is that Maxwell did not live to see most of these advancements. He did not witness radio, television, radar, satellites, Wi-Fi, smartphones, or medical imaging. He never watched a rocket launch or saw an astronaut send a message from orbit. Yet every one of these achievements traces its origins to the invisible waves he predicted through pure reasoning. It shows the power of theoretical science, the idea that a concept discovered on paper can transform the entire physical world. The societal impact cannot be overstated. Maxwell's waves have become the carriers of human expression. They transmit voices, images, emotions, knowledge, and creativity across borders. They enable rescue missions, support hospitals, guide airplanes, connect families, and provide education to millions. The invisible highways he uncovered have become essential to human existence. Even the world economy relies on financial information sent across electromagnetic networks. Remove Maxwell's contribution, and the modern world collapses instantly. At a deeper level, Maxwell's prediction altered humanity's perception of nature. His work revealed that the universe is not just a space filled with objects, it is filled with fields that interact, propagate, and influence everything. This concept inspired generations of scientists, from Einstein to modern engineers. It changed how humans interpret light, energy, motion, and information. The prediction of electromagnetic waves became one of the clearest demonstrations that mathematics can reveal truths hidden from direct experience. His work remains a testament to the power of human intelligence, a reminder that a single mind, armed with curiosity and insight, can alter the course of history without ever touching the devices that future generations would rely on. Maxwell showed that understanding nature's invisible processes could unlock unimaginable possibilities. Today, as the world hums with billions of wireless connections, as satellites orbit above, and as information flows across continents, we are living in the ongoing echo of Maxwell's prediction. When we say that James Clerk Maxwell laid the groundwork for technologies like radio, Wi-Fi, and modern electronics, we are acknowledging a truth that stands at the core of modern civilization. It means that long before a radio ever crackled with sound, before Wi-Fi signals connected the world, and before electronic devices became central to human life, Maxwell had already written equations and conceptual frameworks that made all these inventions possible. His contribution was not simply a single discovery, but the unveiling of a complete blueprint, a unified scientific foundation describing how electricity, magnetism, and light interact. This foundation has guided every major technological revolution that uses electromagnetic waves. To understand how deeply Maxwell's work shaped today's world, imagine modern life without the technologies we depend on every day. No radio broadcasts, no mobile phones, no wireless internet, no GPS, no radar, no microwaves, no fiber optic communication, no television signals, no Bluetooth, no electrical engineering as we know it. All of these rely entirely on the principles Maxwell revealed in the mid-19th century. His famous Maxwell's equations predicted that electromagnetic waves made of oscillating electric and magnetic fields, could travel through space at the speed of light. This single insight became the foundation for the entire field of electromagnetic communication. Before Maxwell, electricity and magnetism were studied separately, almost like different worlds. Scientists knew that magnets created mysterious invisible forces, and that electric charges could create jolts or sparks, but the connection between these phenomena was unclear. Maxwell changed this forever by uniting them into one elegant theory, electromagnetism. His equations described how electric fields generate magnetic fields, and how magnetic fields generate electric fields, creating waves that propagate through space. It was this description that allowed future inventors to generate, transmit, detect, and manipulate those waves, precisely what radio, Wi-Fi, and electronics are built on. When Maxwell mathematically demonstrated that light itself was an electromagnetic wave, he delivered one of the most profound insights in scientific history. He showed that visible light, infrared, ultraviolet, radio waves, microwaves, and even X-rays were not separate types of phenomena, but part of a single electromagnetic spectrum. This discovery meant that if humans could learn to produce and control other parts of this spectrum, entirely new forms of communication and technology would become possible. Maxwell didn't build radios or wireless devices himself. That came later, but he provided the scientific map that made those inventions inevitable. The first major breakthrough built on Maxwell's work came from Heinrich Hertz, who generated and detected the electromagnetic waves that Maxwell predicted. Hertz proved Maxwell's theory experimentally, showing that radio waves behave exactly as the equations described. But even Hertz initially believed his discovery had no practical use. It was Guglielmo Marconi, inspired by Maxwell's vision and Hertz's proof, who developed the first radio telegraphy systems. Without Maxwell's theoretical foundation, Marconi would never have known what kind of waves he was working with or how to manipulate them. Radio communication changed the world by allowing information to travel wirelessly over vast distances. Ships at sea, military units, emergency responders, and ordinary citizens could suddenly communicate across continents. Yet this was only the beginning. Maxwell's equations guided later scientists as they explored other regions of the electromagnetic spectrum, leading to television broadcasting, radar systems in World War II, satellite communication, and the digital revolution of the late 20th century. Today's Wi-Fi technology is perhaps the most direct descendant of Maxwell's ideas. Wi-Fi networks use radio waves, specific frequencies within the electromagnetic spectrum, to transmit data between devices. Every time a smartphone connects to a network, every time a laptop receives a signal from a router, the process follows the exact same laws Maxwell wrote down. Wi-Fi uses modulation techniques, wave propagation, and field interactions that map perfectly onto Maxwell's theoretical predictions. In essence, your wireless router is an applied demonstration of his equations in action, billions of times every day across the world. Modern electronics also owe their existence to Maxwell. Whether it is the circuits inside computers, the components inside smartphones, the antennas in GPS receivers, or the sensors in medical devices, all depend on electromagnetic behavior. Even microprocessors, which seem purely digital, operate using tiny electric fields guiding electrons through microscopic pathways. Semiconductor physics, transistor operation, integrated circuits, and communication chips all rely on electromagnetic principles. Engineers use Maxwell's equations to design antennas, optimize signal transmission, prevent interference, and ensure that devices function correctly. Consider a microwave oven. It heats food using microwaves that excite water molecules. Consider MRI machines in hospitals. They use powerful magnetic fields and radio waves to image the human body. Consider solar panels. They convert light and electromagnetic wave into electricity. Consider Bluetooth, 5G, and satellite internet. They use sophisticated modulation of electromagnetic waves to carry digital information. All these technologies depend directly on Maxwell's revelations. His work acts as the common heartbeat of the modern technological era. It is often said that Newton explained how the planets move, Einstein explained how space and time work, and Maxwell explained how the entire modern world communicates. This is not an exaggeration. Maxwell's equations allow us to understand how energy travels, how signals propagate, and how forces interact at every scale. His theory is the foundation for electrical engineering, applied physics, telecommunications, signal processing, and countless modern industries. Every time you turn on a light, unlock your phone, use the internet, listen to the radio, watch television, or check the weather using radar, you are witnessing Maxwell's impact. Thus, when we say he laid the groundwork for technologies like radio, Wi-Fi, and modern electronics, it means that Maxwell's genius provided the invisible architecture that supports nearly all wireless communication and electrical innovation. His vision expanded the limits of human knowledge and opened doors to discoveries no one in his time could have imagined. He transformed abstract mathematical ideas into a universal framework that powers the devices, networks, and systems we use every day. Maxwell didn't just influence modern technology, he made modern technology possible. In this sense, Maxwell was not only a scientist, but a silent engineer of the future. His equations are woven into the fabric of society, enabling the interconnected world we now take for granted. Every message sent wirelessly, every electronic signal transmitted, and every technological leap in digital communication pays quiet tribute to the mind that first understood the language of electromagnetic waves. Maxwell wired the modern world long before wires, or wireless signals, ever existed. James Clerk Maxwell's research on color vision was not just a theoretical exercise in understanding human perception. It was a foundational breakthrough that transformed the way we capture, manipulate, and reproduce images. Before Maxwell, color perception was largely considered a subjective experience, something personal and variable, and the scientific understanding of how the human eye perceives color was rudimentary. Maxwell approached this problem with a combination of mathematical precision, physical experimentation, and innovative thinking, creating a bridge between the abstract world of physics and the tangible world of visual experience. At the core of Maxwell's work was his study of the way light interacts with the human eye. He recognized that the eye contains three types of color, sensitive cells, each responding to different wavelengths of light, what we now call the trichromatic theory of vision. By understanding that all visible colors could be recreated through combinations of three primary colors, red, green, and blue, Maxwell provided a systematic framework for representing color. Scientifically, this insight alone was revolutionary because it turned color from an elusive quality into a measurable, reproducible phenomenon. Maxwell's most famous experiment in color vision, conducted in the 1860s, involved projecting three black and white photographs of a tartan ribbon through red, green, and blue filters. When these filtered images were combined using a third projection apparatus, they reconstructed the ribbon in its natural colors. This was the first demonstration of color photography, and it effectively proved that color could be synthesized from primary components. His approach was not merely artistic. It was deeply scientific, relying on precise measurement, controlled experimentation, and careful observation. It demonstrated that the principles governing human color perception could be applied to technological reproduction of images. The implications of Maxwell's work extended far beyond photography. By establishing the trichromatic basis of color perception, he laid the groundwork for all modern color imaging technologies. Today, the same principles underpin everything from digital cameras to smartphone displays, from television screens to computer monitors. Every time a digital image reproduces a wide range of colors on a screen, it does so using combinations of red, green, and blue pixels, directly reflecting the insight that Maxwell demonstrated in the 19th century. In essence, Maxwell translated the way humans perceive the world into a language that machines could understand, enabling a seamless interface between human vision and technology. Furthermore, Maxwell's experiments encouraged the development of colorimetry, the science of measuring and quantifying color. Scientists and engineers could now quantify differences in hue, saturation, and brightness with mathematical precision, allowing for standardized color reproduction in industry and science. This was critical not only for photography, but also for printing, textiles, and design, where consistent and accurate color representation became essential. Maxwell's insights allowed these fields to move from trial and error approaches to systematic, reproducible methods, fundamentally changing the standards of visual communication. Maxwell's impact on digital imaging is perhaps the most profound and far-reaching consequence of his research. Every modern digital image, whether on a camera, computer, or phone, relies on principles he demonstrated over 150 years ago. The RGB color model, which is the cornerstone of digital imaging, is a direct descendant of Maxwell's work. Even sophisticated algorithms for image compression, rendering, and manipulation rely on the fact that color can be broken down into quantifiable components that mimic human perception. In this way, Maxwell's theoretical experiments resonate today, embedded in the very devices that define modern life. Equally significant is the influence of Maxwell's work on the development of cinema and television. Early color films used techniques that mimicked his color process, combining images through filters to create naturalistic color. Over time, these principles evolved into the complex systems of digital cinema, broadcasting, and video technology. Even virtual reality and augmented reality systems, which aim to replicate realistic visual experiences, are built upon Maxwell's foundational understanding of color vision. The fidelity and vibrancy of the digital world around us are, in many ways, Maxwell's legacy made tangible. Finally, Maxwell's work on color vision exemplifies the synergy between pure science and applied technology. While his experiments were motivated by curiosity about human perception, the results had immediate and lasting practical applications. By linking physics, physiology, and mathematics, he created a multidisciplinary framework that has influenced generations of scientists and engineers. From photography to digital imaging, from cinema to virtual reality, Maxwell's understanding of color vision continues to shape how we see, share, and experience the world. In conclusion, James Clerk Maxwell's research on color vision was transformative, not merely because it solved a scientific puzzle, but because it provided a practical blueprint for reproducing and manipulating color in the modern technological world. His work bridged human perception and machine capability, giving rise to the digital imaging technologies that define contemporary life. The clarity, precision, and foresight of Maxwell's experiments continue to influence fields as diverse as photography, cinematography, computer graphics, and virtual reality. In every vivid digital photograph or lifelike screen display, Maxwell's vision persists, a testament to the enduring power of scientific insight to shape the practical world. James Clerk Maxwell's introduction of field theory marked one of the most profound shifts in the understanding of physics, fundamentally altering the way scientists conceptualize forces and interactions in the universe. Before Maxwell, the prevailing paradigm for explaining phenomena like electricity and magnetism relied heavily on the notion of action at a distance. In this view, objects could exert forces on one another instantaneously across space without any intermediary mechanism. This approach, though partially effective, was limited in explanatory power and mathematically cumbersome, leaving many physical interactions mysterious. Maxwell's genius lay in his radical reconceptualization of these forces. He proposed that electric and magnetic effects are not instantaneous actions between distant bodies, but are instead mediated by fields permeating space. Maxwell's field theory unified electricity and magnetism into a coherent framework, captured elegantly in his famous set of equations, now known as Maxwell's equations. These equations mathematically described how electric charges produce electric fields, how currents produce magnetic fields, and how changing electric fields can generate magnetic fields and vice versa. By formalizing these interactions as continuous fields existing throughout space, Maxwell transformed the understanding of the invisible forces governing the universe. This was more than a mathematical convenience. It introduced a new ontology of physics, where space itself became a dynamic entity capable of transmitting energy and information. One of the most revolutionary implications of Maxwell's field theory was the prediction of electromagnetic waves. By analyzing his equations, Maxwell concluded that disturbances in electric and magnetic fields could propagate through space as waves traveling at the speed of light. This theoretical insight bridged previously separate domains. Light itself was revealed to be an electromagnetic phenomenon. Suddenly, the nature of light, long a subject of speculation and experiment, was understood in terms of universal laws of electricity and magnetism. Maxwell's insight demonstrated that the cosmos operates according to deep, underlying principles, where fields, not just matter, mediate interactions across the universe. Maxwell's field theory had profound implications for the next generation of physicists, most notably Albert Einstein. Einstein's theory of special relativity, which fundamentally redefined notions of space, time, and motion, drew heavily on the conceptual groundwork laid by Maxwell. Before relativity, the idea of a universal, immutable speed for light was difficult to reconcile with Newtonian mechanics. Maxwell's equations, however, inherently described electromagnetic waves, including light propagating at a fixed speed regardless of the motion of the source or observer. This universal constant became a cornerstone in Einstein's formulation of special relativity. Without Maxwell's theoretical framework, the revolutionary insights of relativity might have remained undiscovered or at least delayed. Furthermore, Maxwell's introduction of the field concept encouraged a more abstract and general approach to physics. Instead of describing forces in terms of direct particle-to-particle interaction, physicists could model the universe in terms of continuous entities that pervade space, influencing matter and energy. This field-centric view influenced not only Einstein, but also generations of theoretical physicists exploring gravitation, quantum mechanics, and cosmology. In essence, Maxwell's fields provided a template for understanding nature in terms of local interactions mediated by underlying structures, a perspective that continues to inform modern physics. Maxwell's work also demonstrated the power of mathematical formalism in physics. His equations were not merely descriptive. They predicted phenomena before they were observed. The subsequent experimental confirmation of electromagnetic waves by Heinrich Hertz validated Maxwell's theoretical insight, cementing the credibility of field theory. This predictive power illustrated a profound truth. Deep mathematical relationships can reveal hidden structures in nature, guiding empirical investigation and technological innovation alike. The influence of Maxwell's field theory extends far beyond theoretical physics into practical technology. By elucidating the nature of electromagnetic waves, Maxwell paved the way for inventions that define the modern world: radio, radar, wireless communication, and even the electrical grids that power contemporary society. Every transmission of data through Wi-Fi, every broadcast on television, and every signal in mobile telephony relies fundamentally on the principles Maxwell articulated. In this sense, the abstract concept of fields directly shaped both scientific thought and technological progress. Maxwell's intellectual courage is particularly noteworthy. At a time when the concept of invisible fields was abstract and unobservable, he insisted on the validity of a theoretical framework that unified diverse phenomena. His vision required imagining space itself as an active participant in physical processes, a radical departure from the mechanistic world, dominant in his era. This imaginative leap laid the foundation for 20th century physics, inspiring Einstein and others to rethink the nature of reality itself. The continuity between Maxwell's field theory and Einstein's relativity illustrates the cumulative nature of scientific progress. Profound insight builds upon prior breakthroughs, transforming understanding across generations. In conclusion, James Clerk Maxwell's introduction of field theory reshaped the foundations of physics. By reconceptualizing electric and magnetic interactions as continuous fields, predicting electromagnetic waves, and demonstrating the deep unity of light and electromagnetism, Maxwell transformed both theoretical and applied science. His work directly influenced Albert Einstein's theory of relativity, providing the conceptual and mathematical tools to reconceive space and time. Beyond its theoretical significance, field theory enabled technological innovations that define the modern world. Maxwell's vision, seeing the invisible structure of reality, remains a testament to the power of imagination, mathematical rigor, and scientific curiosity to illuminate the universe. James Clerk Maxwell's contributions to statistical methods stand as one of the most profound foundations of modern physics and thermodynamics. While Maxwell is often celebrated for his groundbreaking work in electromagnetism, his innovative approach to understanding the behavior of particles in gases introduced a completely new way of thinking about physical systems. Before Maxwell, the study of gases and thermodynamics largely relied on macroscopic observations, pressure, temperature, and volume, without much insight into the microscopic mechanisms driving these phenomena. Maxwell, however, pioneered a method that connected the microscopic motion of particles with the observable macroscopic properties of matter, laying the groundwork for statistical mechanics. At the heart of Maxwell's work in this area was his development of the Maxwell-Boltzmann distribution, a statistical law describing the distribution of speeds among particles in a gas. Maxwell recognized that in a gas, molecules move in a vast array of velocities, colliding with one another in unpredictable ways. Rather than attempting to track each individual molecule, a task mathematically impossible, he introduced a probabilistic approach, calculating the likelihood that a particle has a particular speed at a given temperature. This statistical perspective transformed thermodynamics from a purely empirical science into a predictive framework rooted in fundamental physics. Maxwell's statistical methods revealed deep insights into the nature of temperature, pressure, and heat. For example, he showed that temperature is directly related to the average kinetic energy of particles in a system, providing a microscopic explanation for macroscopic thermal phenomena. Pressure, fastenstone with the extraordinary cerelarly, UNDERSTOOD, as the Zlesians against the RESU, ptes L of a errorless tainter particle collisions against the walls of a container. By connecting particle motion to observable physical quantities, Maxwell offered a coherent framework that unified previously disconnected observations and theories. This approach turned abstract thermodynamic laws into consequences of underlying physical behavior. Maxwell's work on statistical methods also paved the way for the field of kinetic theory of gases, which would later be extended by Ludwig Boltzmann. Together, Maxwell and Boltzmann demonstrated that the seemingly random motion of particles could be described by precise mathematical laws, revealing order within apparent chaos. This shift had enormous implications, not only for physics but for chemistry and engineering, providing a rigorous basis for understanding chemical reactions, diffusion, viscosity, and heat. Conduction. Maxwell's probabilistic approach allowed scientists to predict how gases would behave under various conditions, rather than relying solely on empirical measurements. One of the most revolutionary aspects of Maxwell's statistical methods was their implication for the second law of thermodynamics. Previously, the second law, which states that entropy tends to increase, was often viewed as an empirical principle without microscopic justification. Maxwell's statistical reasoning suggested that entropy emerges naturally from the probabilistic behavior of large numbers of particles. In essence, disorder arises not as a mystical property of matter, but as a statistical inevitability in systems containing many interacting components. This insight connected the microscopic world of molecules with the macroscopic laws of thermodynamics, providing a deeper understanding of why heat flows from hot to cold and why certain processes are irreversible. Maxwell's influence extended beyond classical thermodynamics into the broader realm of modern physics. His statistical methods inspired subsequent developments in quantum mechanics and statistical mechanics. For instance, the concept of particle distributions laid the foundation for the study of fermions and bosons in quantum statistics. Understanding the behavior of large ensembles of particles remains central to modern condensed matter physics, astrophysics, and cosmology. Maxwell's probabilistic approach continues to inform how scientists model complex systems, from stellar atmospheres to semiconductor materials. In addition to its theoretical significance, Maxwell's statistical perspective had profound technological implications. Engineers and scientists could now design systems engines, refrigeration units, and later electronic devices based on predictive calculations rather than trial and error. Understanding particle distributions and kinetic behavior allowed for optimization of energy, transfer, efficiency, and thermal management in practical applications. This bridge between theory and application exemplifies Maxwell's genius. He never divorced abstract mathematics from physical reality, and his methods enabled tangible progress in technology and industry. Maxwell's probabilistic insights also encouraged a more philosophical reconsideration of physical laws. By demonstrating that the laws of thermodynamics emerge from statistical behavior, he challenged the notion of determinism in classical physics. Even if each particle obeys deterministic laws, the collective behavior can appear random and probabilistic. This understanding anticipated later developments in chaos theory, quantum uncertainty, and complex systems. Maxwell, therefore, was not merely a physicist calculating particle speeds. He was a pioneer reshaping the conceptual foundations of how scientists think about nature itself. In summary, James Clerk Maxwell's introduction of statistical methods transformed physics and thermodynamics by connecting microscopic motion to macroscopic phenomena. Through the Maxwell, Boltzmann distribution, and the kinetic theory of gases, he provided a mathematical and conceptual framework to understand temperature, pressure, and entropy. His work laid the foundations for modern statistical mechanics, influencing the development of quantum mechanics and the study of complex systems. Moreover, Maxwell's insights bridged the gap between theory and technology, enabling practical advances in engineering, energy, and materials science. By revealing the hidden order in particle motion and demonstrating the power of probabilistic reasoning, Maxwell not only advanced science, but also reshaped our understanding of the natural world, leaving a legacy that continues to guide physicists and engineers today. James Clerk Maxwell, often celebrated for his theoretical brilliance, left a legacy that quietly underpins much of the modern technological world. While his name may not appear on consumer electronics or in headlines, The principles he formulated in the 19th century form the invisible backbone of the devices and systems that define contemporary life. Maxwell's contributions were both profound and foundational. From his unification of electricity and magnetism, through his statistical methods in thermodynamics, to his insights into light and color, his work laid the groundwork for technologies that we now take for granted. Maxwell's electromagnetic field theory is one of the most consequential contributions in this regard. His famous set of Maxwell's equations mathematically unified electric and magnetic phenomena, predicting the existence of electromagnetic waves that travel at the speed of light and form the basis of modern communications. Today, radio, television, Wi-Fi, and cellular networks all rely on principles Maxwell first formulated over 150 years ago. The signals that allow us to make phone calls across continents, stream movies instantly, or access the internet on smartphones are direct applications of the behavior of electromagnetic fields that Maxwell described. Without his theoretical groundwork, the digital communication revolution that defines the modern world would not have been possible. Similarly, Maxwell's work on color vision and the trichromatic theory of perception quietly powers the visual technologies we depend on daily. Digital screens, cameras, and television displays all rely on the principle that all colors can be reproduced through combinations of red, green, and blue light, a principle Maxwell demonstrated experimentally in the 1860s. Every high-definition photograph, every video call, and every streaming service uses technology that depends on his early insights into human perception of color. While the devices themselves may be modern, the scientific principles guiding their operation were formulated by Maxwell in the Victorian era, highlighting the enduring practical significance of his research. Beyond communication and imaging, Maxwell's contributions to statistical physics and thermodynamics have shaped the world in less obvious but equally profound ways. His introduction of statistical methods to describe the motion of particles in gases, the Maxwell-Boltzmann distribution, enabled later developments in statistical mechanics and kinetic theory. This understanding allows engineers and scientists to design engines, refrigeration systems, and even semiconductors with predictable efficiency and performance. In effect, the smooth functioning of power plants, heating and cooling systems, and modern electronics depends on Maxwell's insights into the probabilistic behavior of particles. Maxwell's influence is also deeply embedded in the realm of modern electronics and computing. The very principles of electricity, circuits, and electromagnetic wave propagation that underpin computers, smartphones, and satellites originate from Maxwell's work. For instance, every processor, from the smallest microchip to the largest supercomputer, depends on the controlled flow of electrons, an understanding rooted in Maxwell's equations. Wireless communication between devices, from Bluetooth to satellite internet, relies on predictable electromagnetic interactions, again tracing back to Maxwell's vision of fields and waves. In short, the digital and connected world that underpins global commerce, communication, and entertainment is Maxwell's intellectual legacy in action. Moreover, Maxwell's contributions laid the foundation for further revolutionary scientific discoveries that themselves have technological impact. Albert Einstein's theory of relativity, for example, was influenced by Maxwell's formulation of electromagnetism. GPS technology, which millions of people depend on every day for navigation, is based on relativistic corrections to satellite timing corrections that are conceptually connected to Maxwell's field theory. The chain of scientific influence from Maxwell to Einstein to modern applications illustrates how theoretical insights, though quiet and abstract, cascade through generations to produce tangible technological benefits. Even in emerging fields such as quantum mechanics, Maxwell's quiet influence persists. His statistical methods and field concepts directly informed the development of quantum field theory, which underlies modern electronics, lasers, and photonics. Technologies that power everything from fiber optic communications to medical imaging devices like MRI machines trace their intellectual heritage back to Maxwell's pioneering work. His contributions were not only foundational for the 19th century, but continue to shape the technological landscape of the 21st century in ways that are often invisible to the general public. Maxwell's work is a testament to the enduring power of theoretical science. Unlike inventors who create tangible gadgets, Maxwell's genius was subtle and abstract. He formulated laws and principles that could predict phenomena not yet observed. This quiet nature of his contributions makes them all the more remarkable, because while Maxwell himself did not directly create devices, his insights made the creation of countless modern technologies possible. In a sense, Maxwell's influence is everywhere but seen by few, woven into the electromagnetic waves, the digital screens, and the circuits that constitute daily life. Furthermore, Maxwell's approach to science, combining rigorous mathematics, careful experimentation, and visionary thinking, serves as a model for innovation across fields. His ability to foresee connections between seemingly unrelated phenomena, whether linking light to electromagnetism or particles to thermodynamic behavior, demonstrates the deep power of abstract reasoning in producing practical results. The technologies that power modern society, wireless networks, digital imaging, energy, efficient systems, are silent witnesses to Maxwell's foresight. In conclusion, James Clerk Maxwell's quiet contributions continue to power the technological world we depend on today. From the devices that transmit and receive information instantaneously across the globe, to the screens and cameras that capture and reproduce color, to the engines, electronics, and systems that drive modern life, Maxwell's principles form an invisible yet indispensable foundation. His brilliance was not in crafting gadgets, but in revealing the deep laws of nature, providing humanity with a toolkit to transform theoretical understanding into practical technology. Maxwell's work exemplifies how abstract scientific insight, though quiet and often uncelebrated, can ripple across centuries to shape the everyday world in profound and lasting ways.